In our last class, under the main topic of dynamics of rigid bodies, we study about the motion of a center of mass. Today we will see about the some main features of center of mass and perform some examples. So, continue on our topic, that is dynamics of rigid bodies. So, to get some features of a center of mass, it is not necessary for any mass to be present physically at center of mass. So, starting from main features of center of it's not necessary for any mass to be present physically at center of mass. Position of center of mass depends on shape, size and mass distribution of the body. Depends on shape, size and mass distribution of the body. Therefore, center of mass may be within or outside the body. Therefore, center of mass may be within or outside the body. For symmetrical bodies, having homogeneous distribution of mass, center of mass coincides with geometrical center of symmetry. Motion of center of mass is always translative. It's very important that motion of center of mass is always. Next point is, for a body of given shape, position for a body of given shape, position of center of mass depends on distribution of mass and is closer to heavier part closer to heavier. One more thing, position of center of mass does not depend on the frame of reference. For example, center of mass of a ring will always be at its geometrical center irrespective of position of frame of reference. Now other point is, position and velocity of center of mass do not change due to internal forces. It is possible due to external forces only. For example, for two particles of masses m and 2m, which are situated at distance r, the position of mass is at distance r by 3 from particle of mass 2m. If these particles move towards each other due to mutual interaction, there will be no change in the position of center of mass. One more point is that total mass moment of all particles related to center of mass is always 0. That means summation of MIRI, that is the summation of all the internal position factors from origin to the center of mass. Total mass moment of all the particles relative to center of mass is always 0. That means where RA dash is equal to is the position vector of ith particle relative to center of mass, relative to center of mass. And 7 point is that total linear momentum of all particles of the system related to center of mass is always 0. That means MIVI, that is the total linear momentum, VI dash is equal to 0, where VI dash is the velocity velocity vector of ith particle relative to center of mass. Due to this reason, center of mass is called zero momentum frame of reference. Due to this reason only, center of mass is called zero momentum frame of reference. Zero momentum frame of reference. Let us suppose two particles having velocity vectors. For example, two particles having velocity vectors I plus j plus k cap and 2i cap plus 2j cap plus form a two particle system. Their masses are 1 kg and 2 kg respectively. Now find out total linear momentum of system of particles about CM. Now find out total linear momentum of system of particles about center of mass. Solution. Velocity of CM. Velocity of center of mass will be here VCM is equal to 1 I plus j plus k plus 2i plus 2j plus 2k upon m1 plus m2, that is 1 plus 2. So finally, as a velocity of center of mass, what we have 5ik plus 5jk plus 5 upon 3. If velocity of ith particle related to Cm is V dash vector and related to origin O is, and relative to origin O is Vi vector, then from below figure we can say that capital X, capital Y, capital Z, this will be a capital O. This is first particle, this is second particle, this is Vi, this is VCM, this is center of mass, this is ith particle. Vi dash is equal to Vi minus Vc. Vi dash is equal to I plus j plus k minus 5i plus 5j plus 5k upon 3. Vi dash is equal to 3. Similarly, we can say V2 dash is equal to y plus 2j plus 2k minus 12 plus 5j plus v2 dash is equal to I plus j plus k upon 3. Therefore, total linear momentum of particles related to CM will be, therefore, total linear momentum particles related to CM P is equal to m1 v1 dash minus का 2j minus का 2k upon 3 plus 2 into I plus j plus k upon 3. This equals to minus 2i minus 2j minus 2k plus 2i plus 2j plus 2k upon 3. This gives you P is equal to 0, as we already said. So the total linear momentum of particles related to CM will be 0. Next class we will talk about the rotatory motion, and under the rotatory motion we will learn about the angular displacement, angular velocity, angular accelerations. Thank you.